very good afternoon to all of you. Let's start with today's work. We are talking about loudspeakers. We continue to talk about it in this lecture and the next few lectures. Last class we were talking about dynamic loudspeakers, so we'll continue talking about them more. Electromagnetic drivers are the very important component of the dynamic loudspeakers. Today, majority of our content would be centered around this idea, and then we will look at some of the mechanical and electrical characteristics. So, this is the slide. This is the summary of the last lecture. I had shown you an exploded view of the speaker, dynamic speaker. It has a strong bottom plate. It has a magnet has two terminals. One is the ring magnet, other one is a central cylindrical pole. One act as, say, north pole, the ring will act as a south pole. So this, to the magnet, what is attached to are the cone and the coil assembly. You have on this central pole, you have this wire coil assembly or voice coil which is attached, and its vibrations are connected to the cone with the help of the a coil or a spring like arrangement. Normally it is called a spider. It has different interesting shapes, which is finally connected to the cone, which gives the sound out. At the end you might get a dust cap. All put together, the cross section looks like this. This is the central magnet. These are the cross sections of the ring magnet. This is the coil. This is the cone, spider, etc. Last class we have discussed that the large cone has better radiations at low frequencies as they move great volume of air. So if the cone diameter is large, at any time the cross sectional area is large, and therefore the volume of the air moved will be large. However, the large cone diameter and large cross section area will increase the mass, and it will be difficult for such speakers to vibrate fast at higher frequencies, and therefore at higher frequencies they do not comply. You need to go to typically to the smaller speakers. So what are the shapes of the magnet? There are various shapes of the magnets that are employed in the speaker design. Here I'm putting you the cross section of three kinds of magnet. One is a simple slug magnet. It's a cylinder. So this is the basic cylinder over here. Typically the other side, this side, is nothing but your it could be as simple as a soft iron core. So any magnetic flux line that originate will go through this. In fact, the central magnet will magnetize the soft iron, and the magnetic lines will go through this way. So this is the place where the magnetic field is created, in this gap. Here also the magnetic field is created, in which we can place the coil. The other example is a ring magnet. So a ring magnet looks like this, one face north, one face south. Here is the transverse cross section of the assembly. So these are the two parts. The shaded parts are the two parts of the ring magnet, and this is the soft iron core. Again, because of the ring magnet, the core will get magnetized and the magnetic field will be created. Typically this magnetic field in this gap will help in moving the voice coil. A more elaborate arrangement in high-end speakers are these kind of magnets, where the center is north, this is south, all permanent, and they are typically called W magnets. So because any cross section looks like this way. Again, these are the gaps. The gaps are the places where the coil assembly moves. In all the three cases I have shown here, you would realize that the magnetic field is radial in nature. So magnetic field here, here, here in this gap and in this gap, it's all radial. Stronger, in general, stronger the magnet, more efficient the speaker will be. Therefore, the magnet remains one of the most important characteristics in a speaker design. Uh, you need a uniform magnetic field in the center that gives you high fidelity. High fidelity means whatever is the sound input, the speaker must reproduce it honestly at a higher amplitude. So if it is doing it, if it is not distorting it, then we call it as a high fidelity speaker. So together these two, efficiency and fidelity, determines the quality of the speaker. So if any one of you doing the project on speaker design, you can think about these two parameters. What is the efficiency? What is the fidelity? At least the fidelity part you can do it using Audacity. Speakers in a speaker design, magnets are generally the costliest component. Remember, they are very important. Their design, the magnetic field strength, and how long they will last. Typically, a good quality speaker lasts for years. I had bought one speaker around 15 years back. That one is still working and around. The other speaker, which I had bought like 4 years back, still working in a very mint condition. So generally the magnets last for a long time. They are high quality magnet, but they are expensive too. Then the second interesting part that we can discuss briefly is the suspension. Suspension is, as I said, this is the cross section, shaded part is the magnet. This is the cross section of the coil. It curves around and around and around and around like this. I've shown you the cross section. Remember, the coil assembly is connected to the cone, to the magnet, and the coil cone assembly is connected to the magnet by the help of a spring-like flexible arrangement, which is normally referred as spider. It may look like this. So this is the outer section where the cone is attached, and this is the inner section where the magnet is attached. So it can vibrate back and forth. So when it goes out, it looks like this. It can come in, it can become in plane. So this is normally referred as suspension. Suspension has multiple functions. It supports the cone, because otherwise the cone will not be held symmetrically and cone will not remain free to vibrate. It keeps the coil at the center. Remember, the coil should not get distorted. It's a very delicate arrangement here, and it provides the restoring force. So as the coil vibrates back and forth, the restoring force is provided by this assembly. Then simply, when the power is switched off or when the source of sound is switched off to a speaker must stop producing sound. That means the vibrations of the cone must die out quickly. That means there has to be some sort of damping. So that damping is provided by this spider or a suspension or spring-like arrangement, whatever you call it. So that is the mechanical damping. How does the magnetic field creates vibrations? So it's a very straightforward. We employ what is called Faraday's laws. The force on a current carrying conductor in a current carrying wire in a magnetic field, if you all know, it is BLI sine theta, where theta is the angle between the current and the magnetic field. If I put the current and the magnetic field at an angle of 90 degree, so in that case sine 90 is 1 and the force acting is BLI or BIL, whatever you call it. This force direction is typically given by the cross product of magnetic field, the current direction and the magnetic field direction, or it is also given by the right hand rule. The right hand rule says that take your right hand, stretch the three fingers in three perpendicular directions as it is shown in the figure. If the index finger points in the direction of current, the middle finger points in the direction of magnetic field, then the thumb will point in the direction of force. So the coil will experience a force. So this is a magnetic field. You pass a current through the coil will force in experience of force in this direction. Now think about it carefully. If the coil experiences a force this way, then the coil will move out. Okay, coil will tend to move out. What will happen if I reverse the direction of current? So if I reverse the direction of current, then the force direction will be reversed this way, and the wire or the coil will tend to move inward. Now just imagine what will happen if this is an alternating current. What is an alternating current? A current which keeps flipping its direction. Why are we assuming alternating current? Because we know that all sound wave patterns, if you use Fourier analysis, you can break it down to a series of sine and cosine waves. So if this current is alternating, that is fluctuates back and forth, then according to this equation, the force will also have the same periodicity as that of I, and the force will also start oscillating, the force will also start working this direction and this direction, making the wire to oscillate back and forth. So the wire will keep oscillating back and forth by using this assembly or this concept. This is how the speakers work. The sound which needs to be fed to the speaker is fed to the wires. The wire is placed in the magnetic field. As the sound current which is proportional to sound in the wire changes its direction, the wire starts fluctuating outward and inward. Entire wire assembly or voice coil starts vibrating, which is attached to the cone. Therefore, in turn, cone also starts vibrating. So this is how the Faraday's laws and right hand rules gives you the direction of the force and the vibrations of the voice coil. Typically in any in any speaker, the coil is cylindrical. Look at this again, cross section. The coil is this red color thing. They're all insulated. What you are seeing here in red color is the red varnish. The entire coil copper wires are varnished nicely and they are wound on this core. If you can see, they are so close you can't see them separately, but they are here. So this is your voice coil. You can see that the voice coil assembly is connected to the cone using this spider arrangement. Okay, these are the magnets. This is the magnet. This is gray one is the magnet, and this is the gap here. This is a W magnet kind of thing. There's a gap here. In this, the coil moves up and down in this diagram. So this is how the coil is suspended in a magnetic field. So there is a magnet here, magnetic field in this gap created. You can recall now, just a while ago I had told you the magnetic field is radial. So magnetic field is along the radially outward or inward direction. The coil is moving up and down. So or the coil is circular. So the direction between magnetic field and the coil is 90 degree. The force acting on it is in the up and down direction. So force moves up and down here. So that is the cylindrical coil, which is kept in a radial magnetic field, and force is along the axis of the cylinder. So axis of the cylinder is vertical This is the direction in which the force will work, either upward or downward, depending upon the direction of current. And the change in the force direction happens according to the frequency of sound that will make the cone vibrate up and down. The force is given by BLI at any instant. Now, remember that you will get a large force. Well, what we want in speaker design, a high fidelity is the aim, that it should faithfully reproduce the sound, and b, what it should do is it should it should faithfully produce the sound. That is the first part. And the second is that for a given speaker design, it should maximize the sound output. That means, if you like, nobody likes large speakers, they take volume at home or at wherever they are placed. It's difficult for them to place, make them mix into the decor of the situation. So we always want speakers as small as possible. They're easy to carry, portable, etc. But remember, the smaller speaker means smaller cone diameter, and therefore the less amount of air displaced, and hence the less volume. So for example, if you are doing in an auditorium some transmission of sound, then small speakers might not be so useful. So the other aim on the speaker design is to produce maximum loudness uh, by smallest possible size. Now, in order to achieve that, one should maximize the force that is working on the coil, because the larger force will push the diaphragm harder to give large sound. So larger force will come if the magnetic field B is strong, and that is achieved by using strongest possible magnets and the smallest possible gaps over here. So magnetic field strong will give you very powerful force on the coil, which will drive the diaphragm of the speaker at a high frequency very easily. The second is that maximizing the length. More is the length of the wire here, circular wire, the more it will be the force. However, the problem with the more length is that its resistance increase, and therefore more power is consumed. So if this particularly becomes an issue if it is a battery operated speaker, like today's Bluetooth speakers and all, portable speakers. So therefore there is a limit of the size on the battery operated speakers. If you want large speakers, then typically battery operated speakers are not feasible. So a lot of power loss also happens. Also, larger L will increase the mass and inertia. That also uh, decreases the frequency, which I'm going to come to in a while. So that also decreases the highest cutoff frequency over which the speaker operates smoothly. So these are the issues. For a given cross sectional areas, remember the circular uh, for a given perimeter or given cross sectional areas. Well, for a given cross sectional area, circle is the smallest perimeter. So if one can use a different kind of design of the coil, maybe a square or maybe a rectangle, by which for the same cross sectional area you can have a larger perimeter and hence larger L. So people have experimented with other designs apart from circular, but these constraints remain. So do remember that whenever one designs a speaker, then these are the two driving conditions. One, the force should be maximized because that gives you the highest efficiency. For that, B and L should be large. And the other is high fidelity, which we are going to talk mostly in the next class. The gap coil geometry also plays a very important role. When I say gap coil geometry, I am talking about this particular section only. So if I focus on this particular section, and this is called gap coil geometry. So that's a very interesting. There are two kinds of gap coil geometries. One is called overhung voice coil. Now, as the name suggests, the voice coil is overhung in the gap. It's just suspended in it like this. So this is the one pole of the magnet. This is the ring. If it's a ring magnet, then this is the outer ring. This is a cross section. These are the gaps. This is the coil whose cross section is shown over here. So these are the overhung in a sense that the coil protrudes a little bit on this side out from the gap, from the magnet, and also this side out from the magnet. And what happens over here is coil height is greater than the gap's height, and that makes keeps things very interesting. So as the coil vibrates up and down, as we have seen, it will vibrate along the axis. As the coil vibrates up and down, for small vibrations, and remember, I'm using the word small. For small vibrations, the number of coils in this gap would remain fixed. So if it is, suppose it is 1 centimeter, so 1 centimeter, if it starts here, then from here to here, or if it starts here, then from here to here. So for small vibrations, the number of windings within the magnetic field are constant over the coil's normal excursion range. So if the excursion range is small, the number of coils in this gap would remain the fixed. What does it mean? It means that effective length in the magnetic field is constant, and therefore the force acting will not change because of any distortion uh, here. But what happens if the vibrations are huge? So if the vibrations are huge, suppose this coil goes out like half, it's only half inside the coil. So if the vibrations are huge, the length will reduce in every vibration, and therefore the force acting on it will decrease drastically, and therefore some sort of infidelity or non-linearity comes if the coil exceeds its operational limits. So this is how the coil is this coil is affecting the quality of voice. The non-linearities are not as strong as it will be in the other case. These kind of coil has got higher coil mass and sensitivity is low to medium. This coil has a large width. Because of the large width, the mass reduces. They can drive small frequency diaphragms nicely, but not at high frequency. Typically, such speakers are large in size, cater to the smaller frequency range. What happens if you are targeting the high frequency range? Then we typically use a smaller coil of small thickness. So what happens is the coil has less thickness, its mass reduces, and excursion or vibrations becomes easy at high frequency. Now in this case, the thickness of the magnet is much higher or much larger than the than the thickness of the coil. Coil height is smaller than the gap, and therefore if the coil vibrates, for a faithful reproduction, the coil has to stay within this limit. So the magnetic flux that the coil experiences remains constant over the coil's normal excursion range. So for small vibrations, the flux linked with the coil remains same. But what happens if the vibrations are large? So if the vibrations are large, then it will start going out of magnetic field partly on this side, partly on this side. And in that case, you get lot of linear non-linearity in the vibrations, and that typically gives, here the non-linearities are much stronger than the non-linearities that you will get in case of the earlier type of coil. These coils have low mass and therefore their sensitivity is medium to high. That means they can vibrate fast and therefore they can be used for high frequency operations. Typically they are expensive and used mainly in high-end speakers. Now coming to the mechanical and electrical characteristics. Remember there is a spring involved. It's a very complicated motion. Remember, the cone is connected with a spring-like arrangement to the coil which vibrates in a magnetic field. So it's a complicated situation. We can simplify by assuming first like a spring mass system. So I can say that the K is the spring constant of the spring mass system, and the compliance, any speaker spring is defined by something called as compliance. Compliance of a speaker spring, and that is C, which is called 1 upon K. Spring constant you are familiar. I believe you will be hearing the word compliance for the first time. So C is 1 over K. Just like any oscillating system, it will always have its own resonant frequency. So the spring mass system has its own resonant frequency, 1 upon 2 pi root K by M, which is equal to 1 over 2 pi root Cm, where C is the compliance. Every oscillating system also has the Q value, which determines height and width of the resonance peak. Typically in speakers we want the smaller Q so that the it's very wide, spectrum is very wide. Q is typically defined as 2 pi f, where f is the resonant frequency, is the same frequency here, into M upon R, where R is the resistance of the coil, or also called as 1 over R root M by C. Just to recall, a very compliant speakers will move easily and have a low restoring force. So that's obvious. Just to recall what Q value is all about. So if this is the bandwidth of the speaker, generally the bandwidth of the speaker is uh, found by finding first the frequency spectrum. You have already done this experiment. This is the frequency spectrum of the speaker. You plot frequencies here, you plot amplitude here, find out the frequency spectrum. Then you draw a line at minus 3 dB from the maximum. So whatever is the maximum, if it is 50 dB, whichever, you draw a line at minus 3 dB. Then minus 3 dB, remember, is the half power point where the intensity drops to half of its peak value. So it is a half power point. At that particular point, this cutoff is called lower cutoff frequency. This is called higher cutoff frequency, and these two, the difference of f1 and f2 is called bandwidth. So Q value is also defined as the resonant frequency divided by bandwidth. So this gives you a fair idea that what large Q and small q will mean. If you want to have a large Q, then delta F has to be small. So in that case, it will be, bandwidth has to be small. It will be a very narrow graph like this. Sharper peaks you will get. That's a high Q. For example, vibrating air columns. So resonance tube experiment or any Helmholtz oscillator will have a very high Q. Smaller Q means your denominator has to be large, so the bandwidth has to be very large. That will give you the Q value to be small. So you will get flatter, relatively flatter peak. For example, no, I don't think resonance tube it has a large Q. Correct example of small Q will be the sonometer or the guitar vibrations. So that's how the Q value correlates. Now, whenever the coil vibrates in a magnetic field, it's a coil moving in a magnetic field. So there will be a self-induction, or there will be an induced EMF in the coil. It is called motional EMF or dynamic EMF. So induced EMF is given as BLV. You are all well familiar with the formula. That is why the word dynamic speaker, by the way, we call these kind of speakers as dynamic speakers because of this V factor coming in. And faster it vibrates, larger the velocity, and larger would be the self-induced. Larger opposition it will receive from the um, larger opposition it will receive by the coil for vibrating. Also, the impedance of the coil, any coil's impedance is given as 2 pi fl. We are well familiar with this formula also in our earlier classes. So as the frequency of operation increase, the impedance will go on increasing and the current will go on dropping. So do remember that the current can drop by two reasons in a coil in a speaker. Number one, when it vibrates with high velocity. Generally, it will vibrate at high velocity when it is at resonance. That means it is at, I'll show you, that means it is at resonant frequency. So at this frequency, it will vibrate. Power transfer is maximum. Vibrations are at a very high velocity, and therefore at this frequency, the impedance will be very high. Here. So self-induction. So impedance will be very high when the velocity is high, and impedance again becomes high when the frequency of operation goes on increasing indefinitely beyond the normal operational frequency of the speaker. So at higher frequency the impedance will increase. So typically the representative graph for impedance versus frequency looks like this in a speaker. So at the resonant frequency, the impedance will rise because the amplitude of vibration becomes huge. That induces lot of voltage, that induces lot of back EMF. So the impedance will increase. Above resonance frequency, typically the impedance will drop, and again it will slowly increase as the impedance will increase because of the 2 pi fl. So this is a typical curve, impedance curve for any speaker. Remember, this is a representative. In some cases, we have done this experiment over a number of speakers in our laboratory. In some cases, this height is much taller. In some cases, this is much less. Typically, this will increase beyond 15 kilohertz as the frequency go beyond 15. Most of the speakers are designed to operate not beyond 10, 12 kilohertz. After that, the operational, because very large speakers I'm talking about, designing large speakers up to 20 kilohertz is very challenging unless you need a very special purpose. Remember that most of the music is played within 10,000 hertz. So for musical purpose, any general purpose speaker is never generated for frequencies beyond, or never manufactured for frequencies beyond 10 kilohertz. Unless you need a very special purpose 20 kilohertz speaker. So if you need that, in that case the frequency rises. So most of the speakers, as the frequency rises, impedance rises, and therefore the graph goes up. Okay. So today we looked at some of the important characteristics of the dynamic speakers. One was we discussed the magnet and magnetic field. Then we spoke about the spider arrangement, which was helpful for us to understand the mechanical and electrical characteristics of a speaker. and we also talked about the geometries by which the voice coil is placed in the magnetic field. We'll continue talking about the speakers in the next class. We can stop here. Thank you.